So in this video we are going to discuss the questions which appeared in thermal and statistical mechanics in GATE 2004 examination. Okay, so let's continue with the first question, for which the statement is: for any process the second law of thermodynamics require that the change in entropy of the universe will be. So here we are going to talk about two important results, and based upon those we will arrive at final result. Okay, so for in thermodynamics we learned that for a reversible process, let delta S it's equal to 0, whereas for an irreversible process, delta S universe, it is greater than 0. So therefore the conclusion that for any kind of process, delta S, the entropy change of universe, it's either going to be greater than 0 or equal to 0. So therefore the option B is the correct one here. It could be either positive or it could be 0. Okay, so let's continue with the next problem. The specific heat of an ideal gas in 3 dimension at very low temperature T varies as. Okay, so here this question can also be discussed in solid state physics also, but basically because the mathematical foundation is based on the results from the statistical mechanics, so that's why I have included this problem here. So at very low temperature, the electronic contribution to heat capacity is proportional to Cb. It is proportional to T only. Okay, so therefore option A is the correct one here. So let's continue with the next problem. The problem is: which one of the following is a first order phase transition? So before we finally arrive at our conclusion, so let me summarize some of the important results pertaining to first order and second order transition. So I will enlist here the example of various first and second order transition, and then we will decide which one is the correct one here. So examples of first order transitions. Okay, the first one is, it's related to ice water system, solid to liquid, and then liquid to vapor, and third one is solid to gas, So all these transitions in ice water system, they involve latent heat, and these are of the type, they are first order transitions. Okay, another examples which can be included in this type of transition is the melting of gallium also. Melting of gallium, wax and sulfur, etc. etc. They fall in such type of transitions. And another example, the sixth one, it is the superconductor to normal metal transition, normal metal transition, but in presence of field, in presence of field. It's important to note this point, in presence of field. It's an example of a first order transition. Okay, so and the general criteria for the validity of first order transition is that there should be a latent heat. So any transition that involve latent heat, that is going to be always a first order transition. And here how we decide that whether it's a first order or second order. So here G, it's continuous, that's a give free energy, continuous, whereas its derivative of G with respect to T and the derivative of G with respect to P. Okay, so this is connected with the entropy and this is connected with the volume basically. So these are going to be discontinuous. I have discussed this the mathematical points in detail in GATE 2003 example, so you can follow that video also. Okay, so here I am only mentioning the examples for the first and second order transition. Okay, so now let's talk about the examples of second order phase transitions. Okay, so the first one is, it is superconductor to normal transition in normal transition in zero field. Okay, when the transition is taking in absence of field, so then it will become a second order transition. Okay, you just make a comparison between this first case and the sixth one that I discussed among the first order transition. So but when the transition is taking in absence of field, then it is termed as the second order phase transition, because here the second order derivative of the Gibbs free energy, they are going to be discontinuous. The second example is ferromagnetic to paramagnetic conversion, paramagnetic transition. This is also an example of a second order transition. And the third one is the important one, that is a liquid helium okay, so that is from helium 1 to 2. So when it converts from helium 1 to 2 at the corresponding to critical temperature of the order of 2.17 Kelvin. So this is also an example of a second order transition. So liquid helium 1, it's called as normal phase of helium, normal phase, and it is the helium 2, it's a superfluid. Okay, so this transition, the transition of helium 1 into 2, this is also called as lambda transition. Okay, lambda transition. And the reason is that when we make a plot between the heat capacity as a function of temperature, so heat capacity as a function of temperature, the kind of behavior it's shown by the heat capacity at the phase transition. Okay, it's a shape, it resembles with the letter lambda. Okay, so that's why it's also called as lambda transition. So at the critical point, okay, so there's a discontinuity in the heat capacity here. So this occurs at temperature Tc. It's not lambda, but it is T as a function of temperature. Okay, so this is an example of a second order transition. Okay, why? Because heat capacity is exhibiting discontinuity as a function of temperature, and heat capacity, this is equal to T ds by dt, where entropy is a first order derivative of G. Okay, so I can write this as minus T d to G S, that is equal to d minus dg by dt. Okay, so dt square. Okay, so because it's the second order derivative which is exhibiting discontinuity, so that's why helium 1 to helium 2 transition is termed as second order transition. So if you just take a look at the options that are given to us, so we have to identify the first order transition. So here vaporization of liquid at its boiling point. So this is the example of first order transition. This is first order normal helium to, so as I just discussed, it is second order ferromagnetic to permanent, it's also second order superconducting to normal state. Okay, and because it's not mentioned and there's no mention of the field, so that means it's, we will consider it as zero field. So superconducting to normal transition in zero field, that is termed as second order transition. So I hope now this point is this point will be clear to all of you. So let's take a look at the next problem. The statement is, an ensemble of n 3-level system whose energies are given as minus E0, 0 and E0, it is in thermal equilibrium at temperature T. So let beta is equal to 1 by kVt. So if beta E0 that is given to be equal to 2, the probability of finding a system in the level E is equal to 0 is, okay. So we can solve the problem 1 with the help of partition function approach. Okay, so here let me draw the energy diagram first. So we are having 3-level system with energies which are given as minus E0, 0 and E0. Okay, and the partition function for this system will be Z, that is equal to exponential minus beta EI. Okay, and because it's not mentioned that these energy states, they are degenerate or non-degenerate, so we will take them as non-degenerate. Okay, so this is equal to exponential beta E0 now corresponding to this level plus exponential beta multiplied by 0. Okay, so that will give us 1 plus exponential minus beta now energy corresponding to third level, which is E0. Okay, so that means that is equal to 1 plus exponential beta E0 plus exponential minus beta E0. Okay, so that is equal to 1 plus 2 cos hyperbolic beta E0. So that is the partition function. Now the probability of energy state E is equal to 0, that is equal to exponential minus beta multiplied by 0 divided by Z, and that is equal to 1 upon 1 plus 2 cos hyperbolic beta E0, because beta E0 is given to us as 2. Okay, so I will replace beta E0 with 2. Okay, and that is equal to 1 plus 2 cos hyperbolic 2 and its power minus 1. Okay, so if you just take a look at the options that are given to you, this is wrong, this is also wrong, this is also wrong. So here in the last one it's 1 minus 2 cos hyperbolic 2 power minus 1. It should be it should not be minus, but it should be the other, it should be plus. Therefore D is the correct option here. So let's take a look at the second problem, which is associated with the same statement. Now we are talking about the free energy of the system at high temperature such that this condition is satisfied, that is beta E0, it's much smaller than unity. So the Helmholtz free energy, once the partition function is known to us, then we can quickly calculate the Helmholtz free energy. So Helmholtz free energy is equal to minus kBT ln Z partition function. Okay, so that is equal to minus kBT, and for n particle system, so we need to multiply by n here. Okay, otherwise what we can do is here, if we take ln Zn, so here Zn is equal to Zn, that is equal to Z1 power n. So when we will take its logarithmic, so ln Zn will be n ln Z1. So that's why I'm taking n here. So ln Z, which is equal to 1 plus exponential minus beta E0 plus exponential beta E0. Now we have to apply the condition that beta E0 it is much smaller than unity. So that means I can write this is equal to minus n kBT ln 1 plus 1 minus beta E0, neglecting higher order term because beta E0 is smaller than unity, so higher order terms will be even smaller than that value. Okay, and then 1 plus beta E0, and then again we will neglect the higher order term. So beta E0 will cancel with beta E0, so we are left with minus n kBT ln 3. Okay, so minus n kBT ln 3. So therefore D is the correct option. D is correct here. So let's take a look at the next problem. This is from black body radiation. The statement is, consider a black body radiation in a cavity which is maintained at a temperature of 2000 Kelvin. Okay, if the volume of the cavity is reversibly and adiabatically increased from 10 to 640 centimeter cube, the temperature of the cavity changes to. Okay, so here because we are talking about the reversible adiabatic expansion of the cavity, and for that particular case, for a cavity undergoing reversible adiabatic change, okay, this quantity will remain constant, Bt cube, that is equal to constant. Okay, this is basically one of the results that we discussed while talking about the black body radiation inside a cavity. Okay, so this result will be valid for reversible adiabatic expansion of the cavity. Okay, so here the information that is given to us, that is V1 is that is initial volume, that is 10 centimeter cube, and T1 is equal to 2000 Kelvin, and V2 is given to 640 centimeter cube, and T2 we have to find. Okay, so by applying this result, so we can write V1 T1 cube, that is equal to V2 T2 cube. Okay, so that means T2 will be V1 by V2 power 1 by 3 multiplied by T1. Okay, so that means 10 divided by 640 power 1 by 3 and multiply by T1, which is equal to 1000. Okay, so this is equal to 1 by 4 into 2000, and that is equal to 500 Kelvin. So therefore D is the correct option here. Now let's take a look at the next problem in continuation with this one. Okay, the equation of state of a dilute gas at high temperature is described by this equation, where V, small v, is the volume per particle and Vt is the negative quantity. So it is given to us as a negative quantity. So one can conclude from this is a property of, so we have to identify the exact option out of the given 4 options. Okay, so for this purpose we will take a look at the real gas equation, which is a van der Waals gas equation. Okay, so here the van der Waals gas equation, P plus A upon V square into V minus V, that is equal to RT. Okay, so for one mole, okay, for 1 mole V, that is equal to Vm. Okay, and that is equal to N multiplied by V, where N is the number of particle. That's the, if we are talking about 1 mole, so that means Avogadro number, the number of particle, and V is the volume per particle. Volume per particle. Okay, so then this equation can be written as P, that is equal to minus A upon B square plus RT upon B minus B. Okay, so let me call this as equation 1. Okay, so now we multiply on both sides with V, so then we obtain PV, that is equal to minus A by B, okay, plus RT B upon B minus B. Okay, so that means I can write in terms of volume per particle, so that is P n multiplied by volume per particle, and that is equal to minus A upon n V plus RT NV upon NV minus B. Okay, because NV, that is much greater than V, so under this approximation I can write that P and V, that is equal to minus A upon NB plus RT, because under this approximation we can neglect this quantity, and finally this will cancel with this, so we are left with only RT here. Okay, so RT can also be written as, if we apply the ideal gas equation, so that is minus A upon NV plus N KB T. Okay, so this can be written as PB, okay, PNB, that is equal to this quantity. Okay, so that means PNB upon NKT. Okay, so I'm by bringing this term into PP, yes, we are taking this as common. Okay, so that means I can rewrite this as PNB upon N KVT, and that is equal to 1 minus A upon, so here we need to multiply by N KVT here, so that will become N square B N square V KVT. Okay, so this can be written as, that is 1 plus B as a function of T upon B, so it is this B, and the remaining BT, that is equal to minus, so here BT, that is equal to minus A upon N square KBT, which is a function of temperature and negative. Okay, so therefore from this property, from this equation, we conclude that this is a van der Waals gas. Okay, and remaining 3 options, they are incorrect. Now let's take a look at the next problem. It's related to the phase transition. Okay, so the problem is in the region of coexistence of a liquid and vapor phases. Okay, so material, so we have to identify the correct option. Okay, so let me draw the diagram first so that we can try to understand this point also. Okay, so if we make a graph between P versus B, so that means we are talking about the isotherms. Okay, so and the isotherm at different temperature. Okay, so once the critical temperature is achieved, so then we encounter a situation something like this in the P versus B curve, or in the isotherm, and this temperature at which such kind of situation where a point of inflection is noticed, we call such an isotherm as critical isotherm. Okay, and then if you further move below this point, so this type of behavior is seen. Okay, so where a flat region in the P versus B curve can be seen, and when you join all these points, the points of inflection. So then we obtain a situation like this. Okay, so this region where a flat feature appear in this P versus V diagram, this contain both liquid and both phases. The region of coexistence, this is the region of coexistence of vapor and liquid phases. Okay, so in this region all these three quantities Cp, beta and kappa T, they are all infinite. Okay, so here in this region of coexistence of these two phases, Cp, that's heat capacity, beta and kappa T are infinite. So therefore D is the correct option here. So let's continue with the last problem from GATE 2004 examination. So here the dimension of phase space of 10 rigid diatomic molecule is. So before we continue with the diatomic molecule, let's continue our discussion with the one single free particle. Okay, so for a single free particle which is moving freely, okay, so it can move in any direction. Okay, so what we need is we require 3 position coordinates for the complete description of its motion. So we require 3 position coordinates, that is x, y and z. Okay, similarly in connection with these 3 position coordinate, we will have 3 momentum coordinates, and which are labeled as px, py and pz. Okay, so in total we require 6 coordinates for a one single free particle, or you can say monoatomic. When we are talking about monoatomic gas molecule, for instance. Okay, so that means, and we say that when you club these position coordinates with the momentum coordinate and the space that we obtain, we call that as phase space. It is a phase space, and for one single particle it is a 6-dimensional. Okay, it has 6 dimension. And when we are having two such kind of free particles, we will the dimension of the phase space will be the number of particles multiplied by phase space of one single particle, which is 6, that is 6n dimensional. Okay, so that means for 2 particles the corresponding phase space dimension will be 12. Okay, now let's try to extend this discussion to a diatomic. For a diatomic but rigid, okay, rigid molecule, rigid diatomic molecule, you can say. Okay, now if we just imagine a single free particle, let's say it's having spherical symmetry. Okay, and then suppose it is rotating in certain direction. Okay, then again we end up with the situation something like this. We cannot distinguish between the initial and final situation for a single monatomic gas molecule. But when we are having a diatomic molecule and rigid, so but rigid, it carries important information. So that means we need not to worry about the vibrational motion of the molecule. Vibrational motion absent. So when it is rigid, so vibrational motion will be absent in that molecule. So that means for a diatomic molecule, so only thing that we need to consider is its translational motion, and then the another one is rotational motion. Okay, so for instance, suppose we are having a situation like this. suppose the gas molecule, it's lying on one of the axes. So this is x-axis, y-axis, and this is z-axis. And let's say the molecule is lying on the z-axis. Okay, something like this. Okay, so now in addition to translational motion, okay, the molecule is capable of rotating either about the x-axis, about the z-axis, and about the y-axis. So these are the additional degrees of freedom you can say. Okay, so that means for translational, the conclusion is that for translation we require 3 position coordinates which are labeled as x, y, and z, and accompanied with 3 position coordinates we will have 3 momentum coordinates which are labeled as px, py, and pz. Okay, and in addition to this we are also having the possibility of rotation. But now the point is that when the molecule is rotating along the z-axis, it will not give rise to an additional type of information, because when it's rotating we will not be able to distinguish between the initial and final position after the rotation along the z direction. Okay, so because it will keep on moving like this. Okay, so that means we will only consider the rotation of this gas molecule only along the x direction and y direction. And if we associate a angle theta that describes the rotation of the molecule along the x direction, theta, and phi along this direction, and in principle for the non-linear molecule you can assign another parameter psi for the rotation of the gas molecule along the z-axis. But here for the case of diatomic linear molecule we will not talk about the psi. So that means to describe the angular rotational motion of the gas molecule we require two more rotational coordinates. Okay, so named as theta and phi, and then so that means we require 2 more angular momentum coordinates. Angular momentum coordinates labeled as p theta and p phi. Okay, so that means in total we are having 5 position coordinates. Okay, so in total per molecule we are having 3 plus 2, that is equal to 5 position coordinates. Here 3 are required for translational motion, for the description of translational motion, and 2 are required for the description of the rotational motion. And corresponding to these 5 position coordinates we require per molecule we require 3 plus 2, that is equal to 5 momentum coordinates. So out of which 3 corresponds to the linear momentum and the 2 corresponds to the rotational momentum. So therefore per molecule we require 10 coordinates, you can say. Okay, so let me introduce a page here so that I can describe it properly. Okay, so therefore in total we require 5 plus 5, that is 10 coordinates. So out of which 5 are position dependent coordinates and 5 are corresponding to momentum. Okay, so therefore phase space of single rigid diatomic molecule is 10-dimensional. It's for one single diatomic gas molecule. So for 10 such diatomic molecule, the corresponding phase space will be 10, the number of gas molecule multiplied by the dimension of phase space of one single gas molecule, so that is 100. So therefore option D is the correct one. So D is correct here. So here D, that is 100.